lecture. Here is a bit the scheme of what I will try to explain today. So I continue with stochastic process for biophysics. First I'll do a review of the master equation. So I'll review concepts that came in the previous lecture and give another example that is useful. Then I discuss what are the waiting times in a Markov process. And now I'll show you that we are able to calculate probabilities of full trajectories. This is something important that I told you. This is all we wanted to calculate in a Markov process. Well, all. It's a lot of information we can calculate. It's the probability of an entire trajectory. Okay? This will be the second part of the lecture. Then I'll show you how to make a simulation of this type of process with the computer. So before here I give you equations, I made a lot of drawings, a lot of illustrations, but it's important for you to know how to simulate this with the computer. And I'll show you, this is not so difficult for you to do it in a laptop. You don't need a supercomputer for this. And finally, if I have time, I'll introduce stochastic differential equations, which will be the next part of the course, which will be probably 2 or 3 lectures, and then I will go directly on models of biophysics. All right, so this is the introduction, and now I'll go to the blackboard. So give me 1 second. Zoom. I don't know how to stop share. Very good. So please let me know if you don't see or you don't hear me, because I don't have now direct contact with you here. So I go to lecture 10. This lecture will be mostly on waiting times. Well, I'll also discuss a little bit currents. So first, currents, waiting times, and path probabilities, etc. So we'll see what else can we go. So first of all, let me do a reminder on the master equation. A reminder of the master equation for Markov jump process. Markov jump process. Okay. Remember, Markov jump process is a process which is continuous in time and discrete space. So the typical model, it's your states 1, 2, 3, 4, 5, etc. And they are connected with rates with different topologies. Okay. Here, as usual, I tell you there will be one rate from 4 to 5. To 1, they could be also like this, and so on. And they could be the reversible transitions. Remember, here they say time is continuous and the state is discrete. So you have a system which is Markovian and is jumping between the different states. Right? What I derived before in my previous lecture was this equation. This is the master equation. So it has a gain and a loss. So you gain from P nu, you go to mu, the destination, and then you have losses from mu. Remember, this W is the transition rate from mu to nu. Okay? This is the so-called master equation. Again, as I told you in the previous class, you can also write this equation in a vector form, like this. So this is a vector in reality. This is a column vector, and each row in the column is a different state. This is a matrix W times this vector. Okay? Very important. This is, again, as I explained the other day, this has solutions that is of the type P of t is P of 0. This is the initial probability vector E to the W. Okay? This is clear from the previous lecture, no? More or less. Okay.
Yes.
Good. Thank you for replying, because otherwise it's good that you switch on your microphone and sometimes say yes, it's enough. Okay. So the next story is that now you can write this as in this way. So in this way, this will be written like this means that d p mu dt. This is a matrix product, so this will be w mu. Okay, let me write it like this: bold w mu nu p nu of t. So this matrix multiplication with a vector means this in components. So this means that you can write this matrix in terms of this one. So this matrix should be in such a way that you get this equation, which is the master equation, right? And the way this is computed is as follows. So this matrix has the following elements: W matrix mu nu equals the transition rate minus, now there is delta mu nu, and there is multiplied by the sum. This is, it will be the escape rate. Sigma. Okay, so if you do this equation, okay, I forgot something, because here there is mu, here there is mu, but then I forgot that I should add a sum here. This is the sum over nu. Okay, when you have a matrix multiplication like here, what you're doing is you're summing. If you want the element mu here, you do w mu nu times p nu, but then you sum over nu. Okay, it's consistent now. It cannot be that I have here p mu, and here there is not a sum over nu, because otherwise the indices don't make any sense, right? So I'm summing over nu here. Okay. All this is to tell you that this matrix that will come here, it has these elements. So this is the transition. This is the transition rate. Rate nu to mu. This is one only when mu equals to nu. These are diagonal elements. And this is the transition rate between nu and sigma. And I am summing over all sigma. This is from nu to mu. This is the escape rate, remember. This is the escape rate. Right. Or I can call it also gamma nu. Right. This looks very mathematical, but what I want to tell you is that if you put this formula here, you get the master equation that I explained the other day. Okay? It shouldn't be very complicated. Now I'll give you an example, and this I think will be clarifying. Okay. The other day I gave you the example of two-state model, which two-state model is the simplest. It's really the zero model of a Markov process. But now, as I said, it's more interesting when you have more than two states, when you have loops. Because when you have loops, the system can be stationary, it can be both equilibrium and non-equilibrium. Okay, so here's an example, and it will be a four-state model. as I said, the topology can be many things. The topology I will give you is just as follows. If I go clockwise, I put a plus. So the transition rate from 1 to 2 is formally would be like this. W to 1, so transition rate from 1 to 2. I will call it K1 plus. Right? Do you follow me in this?
Yes.
Good. Okay.
Professor, it's very small. Somehow it cannot read very well. We cannot read it good.
It's good you tell me. Okay. One second. So I'll make it bigger. Yeah, otherwise, you won't understand it actually. State 1. State 2. This rate, which is okay, let me write it like this. This rate is W 1 to 2. This I call it K1 plus. Can you read it? Put it full screen. Next. Okay, this is K1 plus. 2 to 3 is K2 plus. 3 to 4 is K3 plus, and 4 to 1 is K4 plus. Okay, these are the clockwise transition rates, and now I will define the counterclockwise. This will be K1 minus. Give me a second because I have to check my notation. Yes. This is K4 minus, this is K3 minus, and this is K2 minus. Right? This is a Markov process in continuous time with 4 states in which you can do loops. You can go this way, you can go this way. Be careful here, I put that you cannot jump between 3 and 1 directly, okay? So it's just a network like this. Okay. This is useful for many biological processes. I can show you later examples. But in this example, what you need to know is how to write the master equation. So the master equation is as follows. You can say ddt of the probability vector P1, P2, P3, P4 equals a matrix that is 4 times 4 times P1, P2, P3, P4. Of course, you can use this formula, but as I said in the previous lecture, you can do this master equation just by looking at the rates. Okay. So what do I put first? This is the change of 1 due to 1. So from 1, what can I do? I need an answer from you.
0.
No, that's not correct.
P1 plus.
That's not correct because you can escape from 1. You are in 1
Yes.
and you can escape. Like this and like this. Okay?
No, I meant that only in the first one we will put 0 because we can go from 1 to 1.
Yes, but now it is a rate equation. This is not, be careful, because this is not, this is not a Markov chain. In a Markov chain you will put something here, because you will say, the Markov chain is in discrete time. So in discrete time you can jump from here to here, okay?
Yes.
But now in the rate equation, we don't add this. We assume you can do this in a short time. But what is happening is that there is, in reality, there is escape from 1. And the escape from 1 comes, if you have this equation, P1 dot equals, you have influxes like this. You come K1 minus P2. You can come from 4, K1 minus, K4 plus P4. But you have losses. You can lose probability from 1. You lose with this rate, K1 plus, and with this rate, K4 minus. minus, this is a lost term, K1 plus K4 minus P1. Okay? So there is this lost term. And this lost term must appear in the diagonal, because this is P1 dot a term proportional to P1. So it should be here. Minus, okay, let me call this, I can call it gamma. Gamma 1 is the escape rate from 1. It is K1 plus K4 minus. So from 1 I have minus gamma 1 P1. So this is minus gamma 1. What else do I have? I have from P2 with K1 minus. From P4, K4 plus. And from P3, nothing. There's no connection with P3. 0. Okay? Right. So from P2, it's now the same game all the time. From P2, I escape with K2 plus and K1 minus. K2 plus K1 minus. This is gamma 2. So minus gamma 2. In each state, you have escape rate. So there will be also minus gamma 3, minus gamma 4 in the diagonal. That's what this term is doing. Okay? So you have gamma 3 is K3 plus K2 minus. Gamma 3 is K3 plus gamma 3, 2 minus. And gamma 4 is K4 plus K3 minus. So this comes in the diagonal, all of them. Be careful, this is different to the Markov chain. This is continuous time Markov process. Now for P2, I have gain terms from 1 and from 3. From 1 I come with K1 plus, and from 3 I come with K2 minus. From 4, 0. I cannot jump from 4 to 2. This is 0. Okay. Then to 3, I have from 1, I cannot go. From 2, I can go with K2 plus. And from 4, I can go with K3 minus. Okay. And last, 4, I can go from 1 with K4, K4 minus. From 2, I cannot go. And from 3, I go with K3 plus. Right? So this is it. This is the master equation. And you see, you can find this by looking at the rates involved and doing this type of equations. So to be sure and to do things well, what I recommend you is you first write the rates, then you write the equations for each of the states, and then you write it in a matrix form if you need it. Sometimes you don't need to write it in a matrix form. This is useful to get the eigenvalues and solve the problem. But you could also write the 4 equations one after the other. Right? So now, an important thing is that this is a stochastic matrix, and I told you stochastic matrices for Markov chains, the columns sum 1. But here the columns do not sum 1, they sum 0. You sum minus gamma 1 plus K1 plus K4 plus minus. Gamma 1 is K1 plus K4 minus. With a minus, and you sum these two, this sum 0. You sum this, also sum 0. This sum 0, this sum 0. So, this it's crucial in the end. And this you can see, you can prove it from the formula they give you here. In this formula you can find that the sum of the column equals to 0. You can come here, make this sum, and check yourself. The sum equals to 0. So,
So
yes?
here we are not using the probability because you say the sum of the vertical column should be 0.
Can you repeat?
I say here we are not talking about probability to move from 1 to 2 or 2 from 1.
No, these are rates. So if you see, be careful because in the Markov chain we had here p's. There was no derivative on the left. There was no derivative. Remember, in discrete time, this is a reminder, Reminder, for Markov chains, then t is discrete. And we had something like p of t plus 1 equals a matrix times p of t. You remember this, no?
Yes, sir.
Remember. Go to the examples and you will see here. Here, in the contrary, there is a derivative. You see? There is a derivative. So what comes here is sum of rates, not sum of probabilities. Here there were rates. There were rates because, for example, in the two-state model, you have P1 at 1, P2 at 1. This is time 1. This was a matrix, P1 at 0, P2 at 0. But what do you put here? If you remember, here you have the transition matrix. You have the probability. Okay, let me copy because I think I have it from my previous lecture. No, I don't have it here, but this was the probability to go to 1 from state 0. Here it was the probability to go to 1. No, 1 from state 2. This is 2 from 1. Here it was 2 from 1. Sorry, this is 1 to 2. 1 to 2. And this is probability 2 from 2.
We can't really read what it is written.
You can't read? Okay. Well, you will be able to read in the recording later, but if I make it bigger, in the Markov chain, you have, for example, this one. You have P, 1 minus P, Q, 1 minus Q. We had P1 at time 1, P2 time 1 equals P1 at time 0, P2 at time 0. And what we were putting here was to 1, from 1, you go with 1 minus P. Then you get P, then you get Q, then you get 1 minus Q. We're using this matrix. But what is P exactly here? P is the probability that, okay, this element here, it is the probability that you go to 2 given that you are in 1. And what was 1 minus P? 1 minus P, it is the probability to go to state 1 given that you were in state 1. Do you follow me?
Yes, sir.
Okay, so when you sum the column, the sum of the column is P1, 1 plus P2, 1. Conditional probabilities. So this is 1. You agree with me?
Yes, sir.
But here there are rates. These are not probabilities. So first of all, here I have the derivative. I have P dot. P dot. Here I don't have P dot. I have P. P in the next step. Okay? So this is an equation for the evolution of p in one time step. This is how much p changes in an infinitesimal time. This, on the left hand side, this is very important you understand. This is dp dt. So we have, in the Markov chain, we have this equation. In the continuous time, we have this equation. dp dt is wp of t. The other one was different. Okay, so we have p of t is p of 0 e to the wt. But w is rates. In the other case, we have a similar equation, but w had units of probability because t has no dimensions. In the case of the Markov chain, t is 1, 2, 3, 4. Here, t has dimensions of time. So w is a matrix that has as units rates. There's rates. So I can show you, okay, if I have some time, we could show you why the sum of the columns must be 1. Because, okay, now let me say the following. You have this equation. Okay, here the sum of the columns is 1, but here the sum of the columns must be 0. Okay, this is something you should convince yourself. It's very easy to do from here. Okay, because you have this equation. Oh. Okay, you have partial t of t mu equals. Okay, this is the other case. So this is Markov chain. What we are doing is continuous time Markov. Continuous time Markov. Partial t p mu is the sum over nu with w. This is the matrix w mu nu p. Okay, this is the equation that I wrote here. It's the same as what I'm writing here. Okay, w mu nu are the elements of this matrix. Okay, so now the question is, what happens if I sum over mu here? So if I do the sum over mu of partial t of p mu. Okay, what is this? Partial t can be moved out of this sum. Partial t sum of mu p mu. Okay, and what is this? Can someone tell me?
1.
Yeah, this is 1. So the sum of all probabilities is 1. So this is partial t of 1. And what is partial t of 1?
0.
0, 0. This doesn't depend on time. So the derivative of 1 with respect to time is 0. So if I sum this with respect to mu, this is 0. So this means that if I sum with mu all this, which is partial t mu, mu nu p mu, this must be 0. Okay? So now what I'll do is I exchange the order of the sum. So I do first the sum over nu, and I get p nu outside, and then I do the sum over mu of w mu nu. And this is 0. Because I proved, because of conservation of probability. See? Okay? So on one side, I have this equation. This is the master equation. And what I do is, I say, I make the sum on the left over mu, and the sum on the right on the mu. The sum on the left on the mu, trivially, is 0 because of conservation of probability. So because the sum on the left is 0, the sum on the right must be 0. The sum on the right with respect to mu becomes the sum of nu, p nu, times this. But now, for this to be 0, it must be, is if and only if, the sum over mu of w mu nu equals to 0. Okay? So this means that the sum over the rows of every column must equal to 0 because of conservation of probability. Okay? This is a mathematical way of doing, but the message I want to convey to you is that discrete in Markov chains, the stochastic matrix, this W, the column sum 1. In continuous time, the transition matrix, the column sum 0. Okay? Maybe now it's very abstract for you, but try to do this later at home, and you will see. It's just 2 lines. Okay? So this is conservation of probability. The column sum 0. Right? So with this, I hope I convince you. If not, we will have a Q&A tomorrow, so we can discuss this again. Now I wanted to just review on what are the currents in this system, the probability currents, or what are the something called affinities. Okay, so remember, in this system, I can define a current through this link, also a current through this link, or through this link, or through this link. There are probability currents. There can be probability currents. So, for example, I can define the current from 1 to 2. This is the current. Probability current. How do you get this quantity? Can someone tell me the current between 1 and 2? This must be very easy. You have 1 and 2. So the current from, it's important that this has a direction, 1 to 2. So I sum current when I go from 1 to 2. Right? So there must be a positive term. What is the positive term? The current. Remember, current is like density times velocity.
K1 plus.
P1. K1 plus times P1. That's the point. That's the point. So remember, when you have a current in electrodynamics, you have like rho V, something like this, no? In this context, rho is a probability, and V is a rate, 1 over time. So the positive term coming here is via this connection, okay? This gives positive because when you pass this link in this direction, you sum. And then you have the negative, which goes this way. This is a minus. So all you have to think is like particles moving in this network, and you will sum 1 when you pass like this, and you sum minus 1 when you pass like this. Then, if you want to know the net current, the average current, you just do rho times V. Okay? So it will be rho plus times V plus minus rho minus V minus. In this context, this is P1 times the rate. This will be the rate from 1 to 2 minus P2, the rate from 2 to 1. this will be the current, probability current from 1 to 2. If you want to feel a bit better, because sometimes this happens, you can also write it like this. Maybe this is more organized. P1, W1 to 2. P2, W2 to 1. In other words, this for this model is P1 times the rate that brings you upwards, K1 plus, is P1 plus, minus P2, K1 minus. Okay, that's the current. And very important for you is to notice that the current is time dependent. In reality, we have J12 T because you have K1 plus, this is a number, but then P1 is time dependent and P2 is time dependent. So in reality, you will have a time dependent current. On the previous lecture, I defined the stationary current. So the stationary current, stationary is the limit when t goes to infinity of J1 to 2 t. And what is the limit of P1 and P2 when t goes to infinity? We don't know, it depends on the model. But this is what is called stationary probability. Okay, so this is reality. K1 plus P1 stationary minus K2 plus was K1 minus, sorry, P2 stationary. Remember that P1 stationary is defined as the limit when t goes to infinity of P1t. Alright? You follow me?
I have a question.
Yes.
From what I understand, there is a direction indicated, like from 1 to 2, right?
Yes. Yes.
I was expecting that the other current is from 1 to 4 to 3 to 2.
Yeah, okay. So this is a definition, okay? This is 1 to 2, this one. But
Yeah.
you can define all the other currents, any current you want here. You can also define 2 to 1. Okay?
I mean, why is there the negative sign?
Because it's the net current. Very important, net. It's the net probability current. So if you have particles flowing from here to here, there is a flow, and I count, for example, I count 3 particles per second moving to the left. But then there are 1 particle per second moving to the right. What I want to know is what is the net amount of particles transporting in this direction.
Okay, and we are only considering the two points that are consecutive. I mean, it's possible to go from 1 to 2 through 4 and 3, right?
Sure, but then the current is defined between 2 states only.
2 states on, okay.
2 states. You can have, for example, 1, 2, 3. Imagine you have this network. You can have this, for example. In this case, you could define J1 to 4 and 4 to 1. But if you do like this and like this, you cannot, this is not a current, this is something else.
Okay.
Okay? Current is defined between 2 states. This is a good question. Between 2 states. 2, eh? 3 would be something else. So this is called what is called current in probability books is current between 2 states. This is important. Okay? You follow me now?
Yes.
Okay, and you can do the same game with any two states. So what you can do, you can also define J 2 to 1. What would be J 2 to 1? Anyone? 2 to 1.
Is it just the negative?
Sure. So you will start with this. So it will be from 2, I go to 1. This is positive. And from 1, I go to 2. And this is minus J 1 to 2. Okay? Very simple. Of course, because the number of particles going from 1 to 2, net number of particles, because I'm counting upwards minus downwards, is the same, is the opposite of from 2 to 1. Okay? There's no mystery here. So in general, you can define J mu to nu as nu mu phi mu minus phi. This is the general formula between any two states. This is the general formula for the current. Another important quantity that we can define also is called affinity. And often what we can do is take a link and see how different are the rates. So the current measures the net probability flow. So it uses, I said, the density and the velocity. This is like rho times v. Okay? But you can also have a measure of asymmetry in each of the links. So you can define, for example, this is called the affinity. It could be something like this. A, we could say it like the same, like mu to nu. Affinity can be defined like the logarithm of the rate mu to nu, which is written like this, divided by the opposite, nu to mu. This is called affinity. Affinity. Okay, so in the example I put here, I don't know where to put it. Okay, I think a good way is here. In the example I put in this diagram the affinity. I can define the affinity of this link, this link, this link, and this link. So I could say, for instance,
excuse me, Professor, we cannot read well the affinity formula.
okay, so I give you the example and then you will see. In the example, it will be the logarithm. Okay, I put ln. For me, ln is natural logarithm. Some people call it log, but I put ln. Okay, ln. Okay, there are different conventions. I call it ln, but some people, you will also see it as log. 1 to 2 will be the log of the forward rate divided by the backward rate. So it will be, in this case, k1 plus divided by k1 minus. Okay, that's it. It's the logarithm of this ratio.
Plus with k minus or something else earlier.
Can you repeat?
Yeah, the lectures. I don't remember. Maybe it was the energy.
Yeah. So you can have a system where you put k1 plus like a Arrhenius law, e to the minus beta e, and this is e to the beta e. So when you do the logarithm, this will be related to energy. This is a good point. Okay? This is called the affinity. What I want to explain is that this is the general formula. Here I put logarithm. So in general would be the general formula would be a mu to nu would be the logarithm of w nu divided by w mu nu. Okay, it can be positive or negative. You can take any value. Right? You follow me?
Yeah, thank you.
Okay. So next, what I will tell you is, let's say you have this model, and I will discuss something that is important for related to non-equilibrium and equilibrium. So remember, the stationary state can be equilibrium or non-equilibrium. And in general, we will have probability currents. So J mu to nu will be different to 0. So if I pick any random numbers for these rates, if I put 1, 3, 7, 11, 14, 15, 23, and pi, so these will be numbers, there will be a current circulating in the system, in general. So in general, we will be like this. So the stationary state is not an equilibrium state. It's a non-equilibrium stationary state. This is in general, but there is a very specific case, except when the following condition happens. This is called the Kolmogorov condition, and it tells you the following: the product of the clockwise rates has to be equal to the product of the counterclockwise rates. This is written like this. So this is K1 plus times K2 plus times K3 plus times K4 plus K3 plus times K4 plus, when this is equal to the backward. When this happens, then J equals to 0 for all mu's and mu's. Okay? So what you see is that this is a very stringent condition. This is not what you see in general. Okay? So for example, I'll give you a good example where this is broken. So this is a very, very precise condition for equilibrium. So you need, for example, that you have 1, 3, 1, 3, and 3, 3, 1, 1. That will be equilibrium, for example, that choice. But there is a collection of models which will have this. You see that when this happens, this means that A, which I call cycle affinity, A is the sum of the affinities in a cycle. So I do 1 to 2, 2 to 3, 3 to 4, 4 to 1. This will be A 1, 2 plus A 2, 3 plus A 3, 4 plus A 4, 1. Okay, so this will be logarithm of A12 will be K1 plus divided by K1 minus. This will be logarithm K2 plus divided by K2 minus. The next will be log of K3 plus divided by K3 minus, and the next logarithm of K4 plus divided by K4 minus. I took that formula. Now this. So this is the affinity of a cycle. Next, the sum of the logarithms is the product, is the logarithm of the product. So if we take this out, take this out, and this is this. You follow me? Yes? Okay. So this is the log of K plus, K plus, K plus, K plus divided by K minus, K minus, K minus, K minus. When you have this condition, this is 1, and the log of 1 is 0. So what you get in this condition is that one cycle has 0 affinity. So there is no bias in one direction or in the other. Right? This is a very, very precise condition. And in general, you won't have this. So one example is the following. For example, if I do, and this is used for molecular motors, we'll see later, for some models of enzymes as well. You may have, for example, rate R, 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 and R. So clockwise I go with rate R, and counterclockwise I go with rate S. Okay. In this case, if R is different to S, there is a current. So actually, if R is bigger than S, there is a clockwise current, and the current is homogeneous, so it will be J12 is positive, and with R smaller than S, J12 is negative. Okay, this is an example, but we can do many others. Of course, this is just a network, but we think this will have applications in biology. One example we could discuss is, for example, a receptor that is free or that is ligand bound, and this receptor is in a cell, and when it binds, it can get phosphorylated. So one of the terminals, the receptor, gets phosphorylated. There's a P here. And then you can have also that is phosphorylated and is unbound. This would be a 4-state model with rates. And one can use this type of models to understand the dynamics of this type of system. Okay, you see there are 4 states: receptor free, receptor occupied phosphorylated, and receptor free phosphorylated. This is a paradigmatic model of a biological system that can be explained in this way, with this type of models. Okay, so this is the first part of the lecture. If you don't mind, I will do a short break, and I'll go with the next part, which was the how to do simulations of these models. I think I will skip the part on the path probabilities, but we can discuss it next lecture. So let me do a break of 5-10 minutes, and we continue. Okay.
Okay.
Do you have any question about this? No? Okay. Okay, so I pause and I come in around 5 to 6 minutes, because otherwise the room is... So the next part of my lecture is about waiting time. So what is a waiting time? It is the following. So imagine you have a network of states, etc., and state move. So you have a random walker, Markov walker who is jumping in different states. This could be connected to other states. And I will ask the question on what is the time spent on a given state. For example, move. Okay, so imagine I'm jumping between these states, and then I arrive to mu. And since I arrive in mu, I put a clock. So I start the clock and I wait. I count the time until I leave the state mu. Okay. The question is, what is the distribution of this time? So means you look at the trajectory. Say you have state 1, state 2, state mu. You have jumps. Then you arrive to mu and you count the time, how long I'm in mu, until I jump somewhere else, for example to 2. This is this value of time. Then I jump again to mu and I count the time spent in mu and I go somewhere. So the question now is, what is the distribution for this tau? You do a histogram, P of tau, given that you were in the state mu, which could be, for example, even x mu, versus tau. This is a distribution of times, okay? How do you think this distribution will be? Any guess? Maybe you know it? No idea?
Exponential.
Yeah, sure. Exponential. Yes, so it is an exponential. Okay, it's an exponential. And now, so what will be the parameter of this exponential? So, if I tell you, how can I make this exponential fast? Well, everything will depend on the escape rate, no? So if the escape rate is fast, this exponential will be very short. I will escape fast. If the escape rate is small, means it takes me a long time to escape, this exponential will be wider. So if I define gamma mu, define it as gamma of x mu. Remember, I defined this already. This is the escape rate. Escape rate, which in the end, we know is equal to the sum over all the nodes, all the destinations of the transition rate from mu to nu. Okay? This is when you have a transition rate. But let me call it like this. The only thing I want to say is that this distribution is exponential, and exponential distributions have only one parameter. It's not like a Gaussian that has the mean and the variance. The exponential has only the mean. The only thing you need to know in an exponential distribution. One parameter. So the distribution of tau given given that you are at state mu, is equal to gamma mu e to the minus tau, to the minus gamma mu tau. That's it. Okay? This is all you need to know about this. So, my only question would be, well, first, we can do calculations with this. So, first I show you that this is normalized. So, if you do the integral over tau of p tau given x mu, what is the limits of integration of this integral? Nobody know? Repeat?
0 to positive infinity.
Yeah, so this is a time. It cannot be minus infinity. This goes from 0 to infinity. Now I put this formula, and it's integral 0 to infinity of d tau gamma mu e to the minus gamma mu tau. This integral is trivial because you can do a change of variable. X equals gamma mu tau. So this is dx, and this is e to the minus x. So it's integral 0 to infinity of dx e minus x, which is 1. Fine. So it's a normalized distribution, and the average, you can also do the calculation of the average, is the integral 0 to infinity d tau tau e tau given x mu. You put again this formula, and you can convince yourself this is just gamma mu to the minus 1. Okay, easy. Because usually when you write exponential distributions, you write it like this: e to the minus x divided by lambda divided by lambda. Okay, here lambda is 1 divided by gamma mu. Nothing else than this. Just simple comment. How can we understand that we have an exponential distribution? This is not that difficult because you have to think that you are in a state mu and you stay here for some time, this state. So if you think about discrete time, you will do one jump here, another jump, another jump, another jump, another jump, and at some point you jump somewhere. So this probability density equals to the probability that at time 0 you are in x mu, at time delta t you are in x mu, at time 2 delta t you are in x mu, and at some point you jump somewhere. So at time x and delta t you are not in x mu. Okay. This in the limit of delta t going to 0, because we are in the continuum limit. So what is this probability? This, you can think about it as follows. So I will say, first, in this time step, I don't jump. So in delta t, I don't jump. So, okay, so one thing is, this is conditional. Eh? This is conditional that x0 is x1. In delta t, I don't jump. So it means I have to put the probability to stay in delta t. And this is 1 minus the probability to escape. Right? Do you agree with me? Remember, this is the escape rate times delta t is the escape probability. 1 minus the escape probability is the probability to remain here. This is in one step. In the next step, the same. What is the probability to not jump? The probability to remain. And so on, and so on, and so on. Up to 1 minus gamma mu delta t. And there are 1, 2, 3, up to n jumps. There are n of these. So now I say delta t is small. So what does small mean? In mathematics, you do these limits, delta t to 0. But in physics, what we say is we have to find a dimensionless quantity that is smaller than something. Otherwise, it doesn't make sense. And if you find it here, so we will do now gamma mu delta t smaller than 1. This is what we mean by delta t small. So in physics, you cannot say delta t is smaller than 3. No. Time has units of seconds. So you have to say smaller than what? This has units of seconds minus 1. So this makes sense. So delta t is smaller than gamma mu to the minus 1. The escape rate to the minus 1. This makes sense. So when you have this limit, you can write all this product as, okay, I'm using this, as e to the minus gamma mu delta t times e to the minus gamma mu delta t e to the minus gamma mu delta t. Okay, why did I write this? Can someone tell me about this? Anyone?
Is the expansion of exponential at small quantity?
Yes, it is the Taylor expansion. So when you do e to the minus x, this can be written as 1 minus x plus order x squared. So I'm writing e to the minus gamma mu delta t as 1 minus this. I'm doing it inverse, by the way. But then, when you have this, is e of minus gamma mu n times delta t. And this is time. This is time. Okay, here I forgot there is a normalization constant, because this is not normalized. There is an n here. There is an n minus 1. There is an n minus 1. There is an n minus 1. But what matters is we have an exponential distribution. Right? So this is very intuitive in the end. Of course, be careful on one thing. Waiting time distributions that are exponentials are characteristic of Markov process. If you have a non-Markovian process, not necessarily you have an exponential distribution. Okay? This is a feature of Markov process. Okay, and now this is very useful because we can use this to compute probabilities of trajectories, of full trajectories, which I hope I have some time. But we can also, well, I think I can do this in the next lecture because I think for you, probably it's more important to learn first how to make a simulation. So with this, you know everything because you know how long you wait in one state, and you know where do you wait, where do you jump. So there are two things in a simulation. In a simulation, you want to build a trajectory, you need to know two things. How long you wait, and where do you jump. If you know this, and do this one after the other, you will be able to build these trajectories, because now you say, again, I am in state 2, and I need to know how long I wait, and where do I go. And this will be a sequence of jumps, one after the other, that you will simulate from a computer. How long I wait in one, and where do they go to meet, etc., etc., etc. This was introduced some years ago by Gillespie. It's called the Gillespie algorithm, which I'll try to describe as simple as possible. And you will see things are much simpler than what they look at the beginning. So, simulations, how to simulate continuous time. Okay, Markov jump process. Remember, Markov jump is continuous time. Markov jump processes with, be careful, time independent rates. As I say, all the rates that I put here are time independent. So, for example, the rate from 1 to 2 is 3, but it doesn't change in the simulation. It doesn't change in time. If, for example, I put like a system that is periodically driven, so there is a force that is periodic, the rates could change in time. This is not the models we are using. We are using models where all the rates are fixed in time. They don't change in time. That's why I put time-independent rates. This means you have W mu nu for any transition. Time-dependent rates will be W mu nu of t. And things will be much more difficult in that case. So let me go to this example, which is, for instance, these networks that I'm drawing on the time. This is state nu, whatever. There's some connections between them. So I will present you an algorithm that is very, very popular and simple to do in the computer, that is called Gillespie algorithm, which you can find, it was introduced in chemistry first, in a journal. So this is for the author. Well, I had the great luck to meet him once, Dan Gillespie, in a conference in California. This is the way we write scientific journals. So this is an article in this journal, Journal of Physical Chemistry, 81. This is the volume. On the page, okay, this is the issue. Is issue volume 25 2340 from the year 1977. So Gillespie proposed this as a model to simulate chemical reactions. You have to think that the chemical reaction happens at a random time. So you have two atoms that make a bond, for example, and these atoms are in a container. This takes some time to make the bond. And before it wasn't so clear in physical chemistry that this bond is formed at random times, that there was randomness. It was not so clear. And this paper, when Dan Gillespie wrote it, it was first rejected by a journal. Now, it became, after many years, the most famous algorithm to simulate Markov process. So it's really interesting, the story. So you can read the paper here, and it's very good for you to get used to it. So this is a numerical recipe that allows you to generate trajectories, that the one I show here. It doesn't paint the trajectories, just tells you how to do it. Then it is your work to implement in your computer, which is not difficult, you see, and to draw the trajectories. So we need to know two things. As I said here, every time you make a jump, we need to know only two numbers, or two quantities. One jump? And second, when do you jump? Right? How long I stay in a given state, and where do I go? So, how do we do this? So, where do we jump? Okay, first let me say, when do I jump? So, what is the quantity in the Markov process that will tell me when do I jump? Which quantity do I need to know? I just say it. So, I am here in state 3. When should I jump? Gamma, exactly, the escape rate. For this, if I'm in state nu, let's say I'm in state nu, to know when do I jump, I need to know gamma nu. And how do I choose where do I jump? What do I need for this? Anyone?
The probability?
Yeah, the transition probability. Exactly. You need to know the W from nu to somewhere else. These are the only two things that you have in hand to decide for this. So, to tackle this, we need to do the following. For the first question, what we do is we generate a random number, okay, a random number R, which is distributed from the uniform distribution between 0 and 1. Why do I do this? Is because this number will be a probability. Between 0 and 1 is a probability. Could be 0.1, 10%, 0.9, 90%, and so on. I'll show you now what to do with this number. When do I jump? What we do is you generate a random number, which is tau. You generate the random time, which comes from an exponential distribution. So you have a distribution, and you pick from this distribution a random number. So for example, you have this. This would be, for example, gamma nu. Well, we are in nu here, so gamma nu e to the minus gamma nu tau is this distribution. So I will draw from this distribution, I will pick a random number. Of course, in this distribution, the most likely number is 0, but I could get also this number with low probability. Okay? So, and now, so the main point is the following. Every time you jump here, you throw two random numbers. This R and this tau. The tau is very simple. Wherever it comes out of this tau is the time you will spend in this state. So if it turns out the tau is 1.3 seconds, you will be here 1.3 seconds. Very easy. Now the question is what to do with this R. And this is what I'll try to explain to you. So, okay, first I start with the second to make it easier. So you have R generated from gamma e to the minus gamma tau. And this could be, for example, I don't know, example, if gamma mu is 1 second minus 1, you will have a distribution which has mean 1. This will be tau c of tau. You pick a random number from here and could be R equals to 0.7 seconds, for example. This means that in that jump you stay 0.7 seconds. Fine. This is easy. Here it's a bit more complicated, but it's not that bad. What you need to know is where do I jump from nu. So from nu, I have escape probabilities to 2 and to 1. In general, what I do is I build the probabilities that I go to mu from nu. remember, now I have rates. So rates are not probabilities. Be careful. But I can build. With the rates, I can build the probabilities. And the way I do is as follows. This is W nu to mu. Be careful when I write this, I start from the right. Nu to mu divided by the sum over mu of W mu. Okay. What you see here is that this is the transition rate from nu to mu, and I divide it by the sum of all the transitions from mu to any other nu. So this number is smaller or equal than 1. Because W mu nu is a number, and here I'm summing all the W mu nus. They're all positive. So this number is always smaller or equal than 1. As should be, because it's a conditional probability. Okay, so you have to construct this probability. So again, you can also write this as simply W mu nu, and here gamma nu. Okay. So for instance, here you will have a probability for each one from nu, and this will be W nu divided by W1 nu plus W2 nu, and you will have P, this is example, right? P2 nu equals W2 nu divided by W1 nu plus W2 nu. You see this, when you sum this, is equal to 1. So these are probability to jump to 1 or probability to jump to 2. So all you need to know is this random number 0, 1. If it's smaller than this number, you jump to 1. And if not, you jump to 2. So what you do is you take the real line from 0 to 1, and you do the following. So R is a random number between 0 and 1. So imagine it's 0.7. So you put it here, 0.7. And now you say, what is this? Imagine this is 0.3. So this will be 0.6. So then you have to divide the line in between 0 and 0.3. This is 0.3, which is P1 nu. So the length of this is P1 nu. And this other, sorry, this is very bad. 0.7, okay? 0.7. Okay, let me do it 65 and 35, just to be easier. 0, 35, 0, 65. This is 0, 35. This length. And the rest will be, all this will be 0, 65. So, you draw a random number, you get 0.7, is here, and it's in the region of P2 nu. So there are two regions, the green region.
Excuse me, Professor, we cannot see.
Okay, you can watch it later in the tape, don't worry. Okay, I can draw it bigger. So the idea is the following. You
That
take...
part of the chalkboard that is not visible.
Okay. So, yes, the main point is the following. You take the line 0, 1, and you divide it in segments of the length of the different conditional probabilities. Okay? In this case, there are two segments. You can go to 1 and to 2. So you have to divide this line, this interval 0, 1, in one interval, which is of length P1 nu, and a second interval of length P2 nu. You follow?
Yes.
Okay.
Thank you.
And now you draw a random number, u, which is from the uniform distribution in 0, 1. So you pick a random number and imagine it's 0.1. So then come here. Because the random number is in this interval, you choose to jump to 1. Okay? If the random number falls here, okay, this will be, sorry, this will be jump to 1. If the random number falls here, or here, or here, you will jump to 2. Okay? Because this is a uniform distribution till 0, 1, there will be more points ending in this part, which is bigger. So more times you will jump to 2. So this algorithm will make the job. Will make the job of jumping to 2 with probability 65% and jumping to 1 with probability 35%. Does it make sense to you?
Yes.
Don't worry, because there will be homework for this, so you will be able to do it yourself. And this is, of course, when you have 2 states, you can jump to 1 or 2, but you can have more. This could be more complicated.
I just couldn't understand that the random number falls in there, that part, and it makes the probability to jump to 1 and 2. I couldn't understand what's the rule of that random number.
The rule of the random number is generating an event that has a probability as you want. The probability you want is P nu 1 to 1 and P nu 2 to 2. The way you do it to generate this event, you want to simulate an event with a given probability to go to 1. Okay, for example, 99% to go to 1. The way you do this is you generate a random number within 0 and 1. So this will be in this interval, and you make boundaries of intervals. So if the random number is in all this area, you say I go to 2. Why you do like this? Because this area has area, this interval has length of this probability. So when you draw random numbers, many times the random numbers will end here. This means you will end with this probability here. Okay, I think probably tomorrow in the Q&A you will get it more clear because it's not so easy to explain at the distance.
Yeah, thank you. I think we have seen something like this before, but it's
Could be similar to Monte Carlo.
yeah.
Yes. So imagine you have, for example, this state nu, and there is state 1 and 2 and 3. And this way you have conditional probability of 0.5. This way you go with conditional probability 0.3. And this way 0.2. So you want to flip a coin, and this coin with 50% is 1, with 30% is 2, and with 20% is 3. How you do it is you have the line 0 to 1, and you divide the line in one interval that is 0.5. So this is at 0.5. The next interval is at 0.8. And the next interval is, 0.8, and that's it. One interval, 2 intervals, 3 intervals. The first has length 0.5. The second has length 0.3. And the third has length 0.2.
I got it completely. Thank you.
Okay, perfect. And then you draw the I don't know because
this is
you see
the
that.
main part. In fact, it's doing experiment. It's the result of experiment.
Sure. So every step you draw a random time and a random number, decision 1, and this, given that you know the transition matrices, all the W gives you the transition probabilities and the escape rates. With that, you can generate these trajectories. So there will be homework that will come to you, and I will ask you to do this in any programming language you like. This is important. So, okay, with this I finish this lecture, and I wait for you tomorrow in the Q&A. I'm almost done with the math process, and next I will discuss a little bit stochastic calculus, which is also useful. Yeah, and that's it. So this is all for today.